Rival superpowers once built walls, but in space they built bridges. The 23 unlikely collaborations that launched unmanned space missions to new frontiers reveal how humanity's greatest cosmic leaps began with a handshake. You will discover the hidden stories of how enemies became partners and competitors became teammates to achieve the impossible. How did a simple radio parts swap between two nations unlock the secrets of a comet? What forced a secretive space program to share its deepest discoveries with the world? The journey into the cosmos was never a solo mission. What does it truly take to reach the stars together? That handshake in the void did more than just bridge a political divide. It quietly built the technical bedrock for every robotic partnership that followed. The Apollo-Soyuz test project, while celebrated for its human drama, was fundamentally a feat of engineering diplomacy. Teams from NASA and the Soviet space program had to solve a puzzle that seemed impossible. How do you make two completely different spacecraft, built in secret by rival nations, not just meet but physically connect and communicate? They had to create a universal docking module, a kind of space-age adapter, and agree on common radio frequencies and data formats. This was not merely symbolic. It was the first time such detailed technical standards were shared between the two superpowers. The success proved that shared data and compatible technology were not just an idealistic dream, but a practical reality. This established a fragile but crucial thread of trust, a proof of concept that the machines of competing nations could work in concert. That foundational principle, born from a crude mission, would soon be inherited by purely robotic explorers, setting the stage for a collaboration that would chase a comet through the depths of the solar system. That hard-won knowledge of making different systems work together was about to be tested far from Earth. The European Space Agency and NASA joined forces for an ambitious new quest to send a probe where no spacecraft had ever gone, over the Sun's poles. This was the Ulysses mission, and it was a masterpiece of international engineering. Neither agency could have done it alone. Europe built the sophisticated spacecraft itself, a technological marvel packed with instruments. America provided the mighty launch vehicle, a space shuttle, and its powerful deep space network of antennas to listen for the probe's faint signals from across the solar system. This was a perfect synergy of resources, a true partnership where each side contributed what it did best. The goal was as revolutionary as the collaboration. To break free from the flat plane where all planets orbit, the ecliptic plane, and soar high above the Sun. This unique solar orbit, a feat of celestial mechanics using a gravity assist from Jupiter, allowed Ulysses to see the Sun's poles for the very first time. It gathered data that was simply impossible to obtain from our Earth-bound perspective. Scientists from both continents did not just build the tools, they worked side by side, operating the instrument suites and sharing data and analysis in real time. This open flow of information redefined solar physics, giving humanity its first ever three-dimensional map of the heliosphere, the vast bubble of particles and magnetic fields the Sun blows into space. Ulysses proved that even the most complex orbital puzzles could be solved through shared expertise. It set a powerful precedent, showing that the path to understanding our own star was a journey best taken together. This successful joint venture into solar science demonstrated how a shared, compelling goal could overcome any institutional inertia, perfectly paving the way for a partnership that would look even deeper into the cosmos, beyond our own solar system entirely. While Ulysses was mapping the Sun, two other spacecraft were racing toward the outer planets, their discoveries powered by a different kind of alliance. The Voyager program, iconic American machines, carried a secret ingredient to their success, an international brain trust. Though NASA built and launched the twin Voyager probes, the revolutionary science they performed was the product of a global scientific community. Researchers from the United Kingdom, France, Germany, and beyond were not merely consultants. They were the architects. These international teams designed, built, and operated the very instruments that would peel back the mysteries of the gas giants. It was this collective intellect that identified the first active volcanoes beyond Earth, spewing plumes of sulfur on Jupiter's moon Io. It was their shared analysis that decoded the complex, braided structure of Saturn's rings, revealing a dynamic system of shepherd moons and gravitational resonances. This was an informal, science-first alliance where the quest for knowledge trumped national pride. The most important capital was not financial or political, but intellectual. To make this work, the Voyager program established revolutionary data-sharing agreements. Instead of hoarding findings, the international teams agreed to a rapid, open release of all data, creating a global treasure trove for astronomers everywhere. This policy became the gold standard for international space science, ensuring that every new discovery, from the winds of Neptune to the geysers of Triton, benefited all of humanity simultaneously. Voyager transformed deep space exploration from a national contest into a collective human endeavor, proving that the most profound revelations occur when brilliant minds unite across any border. This powerful model of shared discovery would soon be essential for a far more ambitious rendezvous, one that required the world to chase a single, frozen traveler from the dawn of the solar system. The open data policies of Voyager created a global community of discovery, but the next great partnership would turn its gaze inward, back toward our own changing world. NASA and the German Aerospace Center, known as DLR, joined forces for a mission of profound subtlety and power. Their project was called GRACE, the Gravity Recovery and Climate Experiment. It did not look at light or color. Instead, it measured the invisible, the very pull of gravity itself. To accomplish this, they launched two identical satellites. These twins did not fly alone. They chased each other in a precise formation, separated by about 200 kilometers, connected by a constant microwave signal. Think of it as the most sensitive tape measure in the solar system. As the lead satellite flew over a region with slightly stronger gravity, like a massive underground aquifer, it would speed up just a tiny bit, increasing the distance to its trailing twin. That minute change, less than the width of a human hair, was instantly detected. By tracking these endless, tiny fluctuations in the distance between them, the twin satellites could map Earth's gravitational field month by month, revealing where mass was moving. This was a perfect fusion of strengths. NASA provided the satellite bus, the launch vehicle, and its deep space network for communication. The German team contributed the precise microwave ranging system, the heart of the mission, and led the data analysis. Together, they were not just building a machine, they were building a scale for the entire planet. The data GRACE returned was a silent revolution. It allowed scientists to see the hidden pulse of Earth's water. They could watch underground aquifers shrink from overuse in California and India. They could measure the staggering loss of ice from Greenland and Antarctica, not by looking at the surface, but by feeling the gravitational pull of that melted ice disappear. It provided the most precise measurements of sea level rise ever obtained, revealing the water's actual mass, not just its height. This partnership moved climate science from observation to precise accounting. It showed that the greatest environmental challenges are not confined by borders, and therefore, the solutions cannot be either. By sharing the scientific responsibility, NASA and DLR gave the world a universal tool to understand our home, proving that sometimes the most critical frontier is the one right beneath our feet. While Grace was silently weighing our world, another alliance was reaching across 1 billion kilometers to unveil a ringed giant. The Cassini-Huygens mission to Saturn was a symphony of 3 space agencies, a collaboration so seamless it redefined what was possible. NASA built the powerful Cassini orbiter, a bus-sized spacecraft packed with enough fuel and instrumentation for a 13-year tour of the Saturnian system. The European Space Agency took on the daring task of building the Huygens probe, a robotic adventurer designed to plunge into the thick, orange haze of Saturn's largest moon, Titan. And the Italian Space Agency contributed the spacecraft's large high-gain antenna, a crucial communication dish that would serve as the mission's voice across the vast gulf of space. This was not merely a division of labor, it was a fusion of cultures and expertise into a single, focused team. For decades, scientists and engineers from North America and Europe worked side by side, their desks often in the same buildings, solving problems as one unit. They faced immense challenges, from plotting a 7-year interplanetary cruise to ensuring the Huygens probe would wake from its long hibernation just moments before its fiery descent into the unknown. The payoff was beyond anything they could have dreamed. The Cassini orbiter became our eyes at Saturn, revealing the planet's storms and rings in breathtaking detail. But its greatest discoveries came from its moons. It found towering geysers of water ice erupting from the tiny moon Enceladus, a stunning announcement that this frozen world hid a global subsurface ocean, a potential haven for life. And when the Huygens probe successfully parachuted through Titan's atmosphere, it beamed back the first and only images from the surface of an outer solar system moon. It showed a landscape of rounded, icy stones carved by flows of liquid methane, a world with a hydrological cycle eerily similar to Earth's but built from different chemistry. Cassini-Huygens did not just send back data, it sent back a new reality, proving that ocean worlds are not unique to our own planet. This tripartite mission demonstrated that distributed responsibility and a shared scientific vision could overcome any technical or logistical hurdle. The triumph of looking outward to Saturn's moons with such clarity naturally led to a new ambition to turn our collective gaze inward toward the fiery world that might hold the secrets to our own planet's violent birth. The silent accounting of Grace gave us a scale for our planet, but a new partnership is building a camera that can see through the clouds and the dark. The NASA-ISRO Synthetic Aperture Radar mission, known as NISAR, is a technological handshake between 2 space powerhouses. NASA brings its mastery of L-band radar, a powerful signal that can penetrate dense forest canopies to study the woody structure of ecosystems. The Indian Space Research Organization, ISRO, provides the sophisticated S-band radar, the spacecraft bus that carries it all, and the launch vehicle that will send it into orbit. This is not a simple division of tasks, it is a deep integration, a fusion of 2 distinct technological visions into a single, unparalleled observatory. Imagine a satellite that can measure the most minute changes in the Earth's surface, down to a fraction of an inch, whether it is day or night, rain or shine. That is the power of synthetic aperture radar. By bouncing radar signals off the planet and analyzing the returning echoes, NISAR will create exquisitely detailed maps of deformation. It will watch as earthquakes warp the crust, as landslides slowly creep, and as volcanoes inflate with magma. It will precisely track the devastating loss of ice from the polar ice sheets and mountain glaciers, providing an urgent ledger of climate change. This mission is a testament to a new kind of collaboration. It moves beyond just sharing data to co-creating the very tools of discovery. By pooling their unique engineering strengths, NASA and ISRO are building an instrument that neither could afford or develop as quickly on its own. They are proving that the most complex global challenges, from predicting natural disasters to managing precious water resources, demand a global toolkit. This model of shared technology and purpose is setting a new standard, one where the goal is not just to observe our world, but to understand its every tremor and whisper together. Reaching the solar system's hottest planet demanded a partnership forged in fire. The journey to Mercury is one of the most perilous in all of spaceflight. A descent into a gravitational furnace where the sun's pull is immense and surface temperatures swing between scorching 450 degrees Celsius and a frigid negative 180. No single nation dared the attempt alone, leading the European Space Agency and Japan's JAXA to unite for BepiColombo. This was not merely a mission. It was a technological survival test. To avoid being dragged into the sun, the spacecraft had to bleed off speed constantly. It achieved this through a brilliant combination of solar electric propulsion, a kind of ion engine that provides a gentle but relentless push, and a dizzying series of 9 planetary flybys, using the gravity of Earth, Venus, and Mercury itself as a cosmic brake. This intricate dance was a masterwork of celestial navigation. The two agencies did not just share the ride, they built a mission of perfect scientific symmetry. Europe constructed the Mercury Planetary Orbiter, a spacecraft designed to withstand the blistering heat and radiation while it maps the planet's cratered surface and analyzes its bizarre composition. Japan, a world leader in magnetosphere research, built the Mercury Magnetospheric Orbiter, a delicate octagonal prism tasked with unraveling the mysteries of the planet's weak but puzzling magnetic field. Imagine two separate scientific minds, one focused on the planet's skin and bones, the other on its hidden, dynamic heart. By dividing these colossal challenges according to their unique expertise, they created a whole that was far greater than the sum of its parts. BepiColombo is a testament to how complementary goals can forge unbreakable alliances, proving that the most hostile frontiers can be conquered not by competing, but by combining our greatest strengths. Surviving the inferno of Mercury required this deep synergy, a lesson that would soon be vital for a mission heading toward the solar system's frozen frontier, where another world with a hidden ocean awaited. Sometimes the most profound discoveries are made by looking at something old in a completely new way. The International Cometary Explorer, originally a NASA satellite built to monitor the solar wind, was given a second life and a new purpose through an act of cosmic improvisation. It was already an aging spacecraft, having completed its primary mission, when a unique opportunity emerged. The European Space Agency was preparing its Giotto probe for a daring, high-speed flyby through the heart of Halley's Comet. But Halley was a complete unknown. What would its dusty, gaseous environment be like? Would Giotto survive the bombardment? To answer these questions, NASA performed a feat of long-range reprogramming. They guided the International Cometary Explorer on a new trajectory, sending it on a historic path directly through the tail of a different comet, Giacobini-Zinner. This was not a planned handoff from the beginning. It was a brilliant, reactive partnership born of necessity. The data that came back was a revelation. For the first time ever, a human-built machine was taking direct measurements from inside a comet's tail, analyzing the density of dust and the behavior of its ionized gases. This was the reconnaissance mission Giotto desperately needed. The information was immediately shared with the European team, giving them a vital preview of the conditions their own spacecraft would face. Armed with this new knowledge, they could fine-tune Giotto's approach and instrument settings. The result was a spectacular success. Giotto plunged to within 600 kilometers of Halley's nucleus, capturing the first ever close-up images of a comet's icy heart. This tag-team effort, one spacecraft scouting the path for another, transformed our understanding of comets from distant, blurry specks into dynamic, complex worlds. It proved that a mission does not have to end when its original goals are met, and that the most valuable asset in exploration is often flexibility itself. This spirit of adaptive reuse, of finding new roles for old explorers, would soon be applied in an even more unexpected context, bridging the gap between space science and a community far removed from mission control. The vast emptiness of the ocean became a landing strip for the space age. While rockets soared into the heavens, a different kind of mission was unfolding on the rolling waves, a testament to an unlikely alliance between celestial explorers and seasoned mariners. NASA, the master of orbital mechanics, possessed no fleet. The United States Navy, however, commanded the seas. This partnership transformed naval aviators and ship crews into cosmic retrieval specialists, tasked with a unique and urgent mission, plucking precious cargo from the water. They trained relentlessly for the moment a capsule or a satellite film canister would splash down, often in a remote and unpredictable patch of ocean. The goal was a race against time, to reach the spacecraft before it could sink or be damaged by the elements. This was not a simple pickup. It required entirely new equipment, from specialized helicopters with hoists to sea-going vessels modified for recovery. The procedures they developed were a ballet of precision, locating a bobbing object in a vast expanse, securing it, and bringing it safely aboard. For missions that demanded the physical return of data, like the early Corona spy satellites whose film canisters held images of Earth, or biological capsules carrying plants and insects exposed to space, this recovery was the entire point of the launch. Failure was not an option. This terrestrial-oceanic collaboration reveals a fundamental truth about spaceflight. The mission does not end when the engines cut off. It relies on a chain of expertise that stretches far beyond the launch pad, drawing on skills from seemingly unrelated fields to bring the fruits of exploration home. Just as the Navy's mastery of the sea ensured the success of these early ventures, our next story shows how the success of a multi-billion-dollar space telescope came to depend on the passion of a global community of amateur stargazers. The Hubble Space Telescope became a global eye in the sky because it was never truly owned by a single nation. While NASA built and launched the iconic Observatory, its revolutionary power came from a radical policy of open access. The Space Telescope Science Institute was established not as a private club for American scientists, but as a hub for the world's best astronomical minds. Any researcher from any country could submit a proposal to use Hubble, with time awarded based on one simple criterion: the pure scientific merit of the idea. This broke down the traditional barriers of space science, transforming Hubble from a national asset into a global tool. The result was an explosion of discovery driven by a truly international community. Astronomers from over 45 nations have directed Hubble's gaze, leading to breakthroughs that no single team could have achieved alone. They measured the expansion rate of the universe with unprecedented precision, peered into the nurseries of newborn stars, and confirmed the existence of supermassive black holes in galactic cores. This collaborative spirit was baked into the hardware itself. The European Space Agency provided critical components, including the telescope's solar arrays for power and the sophisticated faint object camera, one of its original core instruments. This international model ensured Hubble's scientific output was maximized, its schedule packed with the most compelling questions humanity could ask. It proved that a telescope is more than just mirrors and glass. It is the collective curiosity of the people who use it. This paradigm of shared infrastructure, where the best tools serve the best ideas regardless of origin, created a legacy far beyond stunning images. It established the operational blueprint for every great observatory that followed, demonstrating that the universe reveals its secrets most freely when the entire world is invited to look. This principle of shared vigilance, born from looking deep into the cosmos, would soon be applied to a far more immediate concern, watching for dangers much closer to home. Two missions, one shared goal, racing toward ancient asteroids millions of kilometers apart. While NASA OSIRIS-REx journeyed to the carbon-rich asteroid Bennu, Japan's space agency JAXA guided its Hayabusa-2 spacecraft toward the diamond-shaped asteroid Ryugu. On the surface, they were rivals in a high-stakes cosmic treasure hunt, but behind the scenes they were partners, forging a new model for concurrent exploration. They shared everything. When Hayabusa-2 arrived at Ryugu a year earlier, its detailed reconnaissance revealed a shocking truth. The asteroid was not covered in fine, sandy regolith as expected. It was a treacherous rubble pile, littered with boulders that made finding a safe sampling site nearly impossible. This critical intelligence was relayed directly to the OSIRIS-REx team, who were still en route to Bennu. Forewarned, they were not caught off guard when they discovered their own target was similarly rugged and hazardous. This was more than just data sharing. It was a continuous, open dialogue. Engineers and scientists held joint meetings to discuss the nuances of the touch-and-go maneuver, that delicate dance of briefly kissing the asteroid's surface to grab a sample. They compared strategies for navigating the weak, unpredictable gravity fields of these tiny worlds. When Hayabusa-2 successfully deployed small rovers onto Ryugu's surface, the team shared the operational challenges and triumphs, providing a real-world test case for surface interaction that informed the entire community. This cooperation culminated in a coordinated plan for the returned samples themselves. Scientists from both missions worked together to ensure their precious cargo, the gravel from Ryugu and the dust from Bennu, would be analyzed in complementary ways. This guaranteed that the combined science would paint a richer, more complete picture of the early solar system than either mission could achieve alone. This was not a reluctant exchange. It was a proactive alliance that recognized a simple truth: competing for knowledge is far less effective than building it together. This Pacific-spanning partnership set a new standard for parallel discovery, proving that even separate journeys can walk the same path. High above the Earth, two different ways of seeing merged into a single, piercing gaze. The CALIPSO mission, a partnership between NASA and the French space agency CNES, was built on a simple but powerful idea. To truly understand our atmosphere, you cannot just take a picture. You must take its pulse. NASA brought its mastery of satellite systems, providing the sturdy spacecraft bus and a sophisticated LiDAR instrument. Think of LiDAR as a laser ruler, firing pulses of light downward and precisely measuring how long they take to bounce back from clouds and tiny airborne particles. CNES contributed a high-resolution imaging infrared radiometer, an instrument that senses heat signatures, adding a crucial layer of temperature data to the observations. This was a perfect fusion of distinct national specialties. The French had deep expertise in the delicate art of atmospheric instrumentation, while the Americans excelled at the robust engineering required for long-duration spaceflight. Together, they created a satellite that could slice through the atmosphere vertically, revealing its hidden layers. Before CALIPSO, climate models struggled with a fundamental uncertainty. How do clouds, which can either cool the planet by reflecting sunlight or warm it by trapping heat, actually behave on a global scale? And what is the precise role of aerosols, those tiny suspended particles from dust storms, pollution, and forest fires? CALIPSO three-dimensional profiles provided the answers. It could distinguish between thin, high-altitude cirrus clouds and thick, low-lying stratus decks. It tracked vast plumes of desert dust crossing oceans and measured the soot from industrial emissions settling in the upper atmosphere. This data was not just interesting, it was essential. It filled a critical gap in our climate models, turning vague estimates into precise measurements and giving us a far clearer picture of the complex forces driving global warming. CALIPSO proved that the most pressing environmental mysteries could only be solved by combining unique technological strengths, a lesson in synergy that would soon be applied to a mission with a far more distant and frigid target. A single spacecraft's impact sent ripples across the globe, not in the void of space, but through a network of observatories and control rooms on Earth. The Double Asteroid Redirection Test, or DART, was a mission with a bold and direct goal: to smash a probe into a small asteroid moonlet and change its orbit. But this was never a solo flight. The success of this first-ever planetary defense test hinged entirely on a worldwide watch party. From the high deserts of Chile to the mountain peaks of Hawaii and the plains of South Africa, a coordinated army of ground-based telescopes turned their lenses toward the distant asteroid system called Dimorphos. Their mission was to act as humanity's collective stopwatch, meticulously tracking the moonlet's path both before and after the dramatic collision. Without their continuous observations, no one could have measured just how much the impact had altered the asteroid's trajectory. This was a global scientific clock ticking in unison, but the eyes on the sky were not the only partners. The Italian Space Agency contributed a tiny but brilliant companion, the Liscia Cube. This small spacecraft hitched a ride with DART and then separated, positioning itself perfectly to capture the stunning, real-time footage of the impact, a plume of ejected material blossoming into space. That visual evidence was priceless, showing the physical effects of the strike in breathtaking detail. And the collaboration does not end there. The European Space Agency is now preparing its HERA mission, a follow-up investigator that will travel to the asteroid system to perform a detailed forensic analysis. HERA will survey the crater left by DART, measure the asteroid's mass, and assess its new internal structure. What began as a NASA-led experiment was transformed, through this web of contributions, into a full-cycle global demonstration of how we might one day defend our planet. It proved that deflecting a potential extinction-level threat is not a task for one nation, but a responsibility shared by all, requiring every resource and every vantage point we can muster. This spirit of collective planetary stewardship, born from the need to protect Earth, finds a surprising parallel in the new frontier of commercial spaceflight, where private companies are beginning to collaborate in ways that once only governments could. The DART mission proved that planetary defense is a global responsibility, but a new kind of partnership is now turning the moon into a bustling scientific outpost. NASA's Commercial Lunar Payload Services Program, known as CLPS, is fundamentally rewriting the rules of exploration. Instead of building its own bespoke lunar landers, the agency acts as an anchor customer, purchasing delivery services from American commercial companies. This single shift creates a cascade of collaboration. Companies like Intuitive Machines and Robotic compete to provide the most reliable, cost-effective landing buses. They handle the brutal engineering of getting to the moon, the terrifying descent, and the communication link back home. This frees NASA to focus on what it does best, developing the sophisticated scientific instruments that will unlock the moon's secrets. But the real genius of CLPS is its open architecture. The lander is not a closed NASA system. It is a cosmic rideshare with spare capacity explicitly offered to international partners. The Japanese space agency JAXA contributes a transformative rover, a small, agile vehicle that can venture far from the landing site to investigate the lunar soil. The European Space Agency provides advanced navigation cameras to guide the lander's final approach. Even the Mexican Space Agency joins the endeavor, sending its first-ever instruments to another world, a set of tiny, revolutionary sensors to study the lunar environment. This creates a three-layered alliance. You have the commercial drive for efficiency and innovation, the deep scientific and financial backing of NASA, and the specialized expertise of global partners, all converging on a single landing site. It is a model that accelerates exploration at an unprecedented pace. By leveraging commercial competition, NASA gets more missions for its budget. By welcoming international instruments, each lander becomes a microcosm of global science. This is not the old way of monolithic government programs. It is a dynamic, agile network, proving that the path to a sustained presence on the moon is paved not by one nation or one company, but by a thriving ecosystem of public and private pioneers working in concert. The James Webb Space Telescope is a cathedral of glass and gold built by the hands of a continent. Its revolutionary power to peer back to the dawn of time was forged not in one nation, but through a pact between NASA, the European Space Agency, and the Canadian Space Agency. This was more than a simple division of tasks. It was a deep integration of financial resources and technical genius on a scale never before attempted. NASA bore the lion's share of the development and provided the launch operations, but its partners brought irreplaceable pieces of the puzzle. Europe contributed the mighty Ariane 5 rocket, a gift of flight that placed the $10 billion observatory on its perfect trajectory. They also built the near-infrared spectrograph, a complex instrument designed to dissect the light from the first galaxies. Canada, a specialist in precision guidance, provided the razor-sharp fine guidance sensor, without which the telescope could not lock onto its targets, and another sophisticated infrared instrument. This distribution of responsibility meant that no single agency had to shoulder the entire staggering cost or the immense technical risk. For 2 decades, thousands of scientists and engineers across North America and Europe worked as a single, distributed team, their efforts synchronized across time zones. They solved problems of cryogenic cooling, perfected the unfolding of a tennis court-sized sunshield 1,000,000 miles from Earth, and calibrated instruments to sense the faintest whispers of infrared light from the edge of the observable universe. The result is an observatory that has already shattered our understanding of cosmic dawn, revealing galaxies that formed earlier than anyone thought possible. Webb stands as permanent proof that the very largest questions, the ones about our ultimate origins, are too vast for any one country to answer alone. This model of shared burden and shared reward spanning the Atlantic finds a powerful echo in a partnership that reached across the Pacific to touch an asteroid. The dream of landing on Mars arrived in a small, innovative package. Europe's first mission to the Red Planet, Mars Express, carried a profound hope, a lander named Beagle 2. The orbiter itself was a triumph of continental cooperation, built by the European Space Agency with contributions from dozens of companies and research institutions across the continent. It was designed to circle Mars, mapping its surface and probing beneath its polar ice with powerful radar. But the heart of the public's imagination was the tiny lander, a British-led project that represented a completely different kind of partnership. Beagle 2 was not a traditional government project. It was a scrappy, inventive endeavor driven by university scientists and commercial companies, a public-private alliance operating on a shoestring budget compared to its American counterparts. Its goal was as bold as its design, to search for direct evidence of past or present life on Mars. The lander was packed with ingenious tools, including a robotic mole that could burrow into the soil and a gas analysis package to sniff out the chemical fingerprints of biological activity. This was a perfect synergy, the large, stable orbiter providing the ride and the communication relay, and the small, agile lander taking the daring leap to the surface. On Christmas Day 2003, the two spacecraft separated. Mars Express flawlessly entered orbit, beginning its long and prosperous career of discovery. Beagle 2, however, fell silent. The lander successfully descended to the surface, but its solar panels failed to fully deploy, blocking its communications antenna. The mission was declared lost, a heartbreaking end to a bold adventure. Yet, even in its failure, the collaboration yielded an immense legacy. Mars Express has become a cornerstone of Martian science, its data used by space agencies worldwide to plan future rovers and landers. The distributed network of European expertise that built the mission proved that the continent could successfully deliver and operate a complex interplanetary orbiter. The story of Beagle 2 and Mars Express is not just one of a lost lander. It is a lesson in ambition and resilience, demonstrating how a regional partnership, blending established agencies with agile academic and commercial innovation, could launch a lasting presence at Mars. This hard-won experience in combining different models of exploration would prove vital for the next chapter, a mission that required the entire world to look toward the sun together. High above the Earth, a mechanical ballet unfolds in the vacuum, a dance of steel and silicon that has transformed the International Space Station into a bustling orbital workshop. While astronauts are the station's heart, its robotic arms are the dexterous hands, and these systems are masterpieces of international engineering. Canada's legendary expertise in space robotics gave us Canadarm2, a sophisticated successor to the shuttle's original arm, capable of walking end over end across the station's truss to move massive components and astronauts with pinpoint precision. But Canada did not stop there. They also built Dexter, a two-armed robotic handyman that performs delicate surgery on the station's exterior, handling tasks too intricate or risky for the larger arm. This mechanical duo represents a national specialty honed over decades, a contribution so vital it became the station's indispensable maintenance crew. Yet they are not alone in this orbital partnership. From Japan comes the Japanese Experiment Module Remote Manipulator System, a smaller, agile arm designed to service the exposed science platforms on the Kibo laboratory, deftly swapping out experiments facing the harshness of space. And from Europe arrives the European Robotic Arm, a unique system that can operate autonomously, installing payloads and transferring cargo with its own set of intelligent eyes and a brain for navigation. Together, these distinct robotic systems form a coordinated workforce, each with its own strengths and home base, but all working in concert under a unified mission control. Their collective labor has launched a silent revolution in access to space. They have gently released hundreds of CubeSats, tiny satellites built by universities and startups worldwide, into their own orbits, democratizing low Earth orbit. They have installed and retrieved technology demonstrations, testing new sensors and communication systems in the brutal space environment. This orbital testbed is proving ground for the robotic scouts we will one day send to the moons of Jupiter and Saturn. The collaboration proves that when nations contribute their unique, hard-won specialties, they do not just add a piece, they create an entirely new capability, a symbiotic mechanical ecosystem that no single partner could have built or operated alone. This model of shared infrastructure, where robotic hands from across the planet work as one, is quietly paving the way for the next great leap, where the line between public mission and private ingenuity begins to blur. A revolutionary spacecraft is flying on nothing but sunlight. The LightSail program, a unique alliance between NASA and the Planetary Society, turned a centuries-old dream into a working reality. This was not a typical government contract. The Planetary Society, a non-profit space advocacy group funded by its global members, took on the daring task of building and managing the LightSail spacecraft themselves. They harnessed the passion and financial support of everyday citizens to prove a radical technology. NASA's role was that of a crucial enabler, providing the precious launch slots on its rockets and offering deep technical consultation from its veteran engineers. This partnership filled a critical gap. Solar sailing, which uses the gentle but constant pressure of photons from the sun to propel a craft, was too experimental, too high risk for a major agency to prioritize with its own limited budget. Yet its potential was staggering, promising propulsion without fuel for missions lasting decades. The success of LightSail-2 in Earth orbit was a quiet but monumental triumph. The small spacecraft, no bigger than a loaf of bread, successfully unfurled a thin, silvery sail the size of a boxing ring. Using only the pressure of sunlight bouncing off that vast mirror, it demonstrated controlled flight, raising its orbit in a way that defied conventional physics. This was citizen-supported science in its purest form, proving that a technology once confined to science fiction could be mastered by a public-private partnership. It validated a new means of travel for future missions to study the sun or hover at unique orbital points. The LightSail story demonstrates that the spirit of exploration is not confined to government laboratories. When a passionate public joins forces with the technical might of an established agency, they can open entirely new avenues into the cosmos, proving that the future of flight can be literally written in light. This powerful model of grassroots innovation finds a parallel in the world of academia, where university labs are building their own bridges to the stars. The thin, cold air of Mars holds a ghost of a former world. Unlocking its secrets required a unique fusion of institutional minds, a partnership between NASA and the University of Colorado Boulder that put a university lab squarely in the pilot's seat of a major planetary mission. The Mars Atmosphere and Volatile Evolution probe, called MAVEN, was built to answer one of science's most haunting questions: where did the Martian atmosphere go? Billions of years ago, Mars was a warmer, wetter planet with flowing water on its surface. For that to be possible, it must have had a thick, protective atmosphere. Today, it is a frozen desert with an atmosphere less than 1% as dense as Earth's. The MAVEN mission was designed to be the detective on the case, to figure out how and when the planet's air was stripped away. This was not a simple contractor relationship. NASA provided the overall mission management, the launch vehicle, and its unmatched deep space network for communications. But the scientific heart of the mission, the brains behind the entire investigation, came from the university's Laboratory for Atmospheric and Space Physics. The university led the science operations team, meaning their researchers were the ones deciding where to point the spacecraft's instruments and how to interpret the torrent of data it sent back. They did not just suggest ideas, they were in command. They also designed and built two of the mission's most critical instruments, including a sophisticated neutral gas and ion mass spectrometer. Think of this instrument as a cosmic bloodhound, sniffing the tenuous upper atmosphere of Mars to identify the specific gases that are escaping and trace their path away from the planet. This division of labor was a masterstroke. It leveraged NASA's immense logistical power for getting to Mars while tapping directly into the world-class, specialized expertise found in an academic setting. The findings were revolutionary. MAVEN discovered that the solar wind, a relentless stream of charged particles from the sun, was the primary culprit, eroding the Martian atmosphere over eons. But it also found that solar storms and ultraviolet radiation dramatically accelerated the process, stripping away gases like a continuous, invisible sandblaster. This data did not just solve a Martian mystery, it gave us a terrifyingly precise picture of planetary evolution, showing how a world can transform from a potential cradle of life into a barren wasteland. The MAVEN mission proved that a university could be more than a supplier of parts. It could be the intellectual leader of an interplanetary investigation, guiding the science from a campus lab all the way to the edge of another world. This powerful model, where academic institutions step up to lead, is creating a new generation of explorers far closer to home. Ice sheets hold a silent record of our changing world. NASA Ice Cloud and Land Elevation Satellite 2, or ICESat-2, is a spaceborne sentinel designed to read that record with a laser's precision. But its most profound discoveries are not made in isolation. They are forged through a vast, international network of scientists braving the planet's most extreme environments. The satellite's instrument is a marvel of photon-counting technology, firing 10,000 pulses of light a second to measure the height of ice and land to within a fraction of an inch. Yet that incredible data would be just numbers without ground truth. This is where the global partnership activates. Research teams from Norway, the United Kingdom, and Germany mount arduous expeditions across the blinding white expanses of Antarctica and the treacherous crevices of Greenland. They traverse the ice on foot and by snowmobile, lugging sophisticated GPS and ground-based laser scanners to the very same spots the satellite passes over. Their mission is to create a perfect anchor point, measuring the ice elevation from the ground to confirm and calibrate what the satellite sees from 600 kilometers above. This is a continuous, painstaking process of validation. The satellite provides the breathtaking global picture, while the international teams on the ground supply the crucial fine print, the reality check that turns raw data into undeniable fact. Beyond this, these polar nations contribute their own complementary data sets, from detailed glacier flow models to atmospheric measurements, weaving a richer tapestry of understanding than any single source could provide. This collaboration transforms ICESat-2 from a mere observer into the central node of a global polar science network. It proves that the most urgent data about our climate is not owned by one country, but is a shared resource, verified by a chorus of international voices on the ice. This model of a satellite as a global hub finds a powerful parallel in a mission that turns its gaze from the frozen poles to the vast, rolling oceans. Water tells its own story, but for the first time we have a satellite that can read every single word. The Surface Water and Ocean Topography mission, known as SWOT, is a technological marvel born from the deep partnership between NASA and the French space agency CNES. Its mission is to do something never before possible, to measure the precise height of nearly every significant river, lake, and ocean on Earth, not just along a single line, but across a wide, detailed swath. It achieves this through a technique called radar interferometry. Imagine two radar antennas mounted on a single satellite boom, separated by a distance the length of a school bus. By comparing the slight differences in the radar signals bouncing back to these two separate ears, SWOT can create exquisitely detailed elevation maps of water surfaces. This is not a solitary scientific endeavor. From the very beginning, hydrologists from dozens of nations were invited to the table. Scientists from Brazil, India, Canada, and beyond helped define the mission's core requirements. What level of accuracy was needed to track a flooding river? How often did a shrinking lake need to be measured to understand its decline? This global brain trust also designed the complex validation campaigns. Teams fanned out across the world, from the mighty Amazon basin to the remote lakes of Siberia, taking painstaking ground measurements to ensure the satellite's orbital data was perfect. Now that SWOT is in operation, its data flows freely to any researcher with an internet connection. A scientist in Nebraska can now track the pulse of a river in Nepal in near real time, watching as monsoon rains swell its banks. An oceanographer in France can study the fine-scale whirls and eddies of ocean currents, phenomena that influence our global climate. This open data policy transforms the satellite from a piece of owned hardware into a true global utility. It empowers local water managers, informs international climate models, and provides an unbiased ledger of Earth's most precious resource. The SWOT collaboration proves that the most pressing sustainability challenges, from managing freshwater scarcity to predicting coastal flooding, cannot be solved by any one nation looking down alone. They require a shared view from above, a collective vigilance over the blue pulse of our planet. This global perspective on a dynamic Earth finds a powerful echo in our next alliance, one that turns its attention from the fluid movements of water to the invisible, energetic storms that erupt from the sun. A satellite built to watch Earth found a new purpose staring directly into the sun's fury. The Deep Space Climate Observatory, or DSCOVR, began its life as a NAS, a concept for continuous global imaging, a solitary sentinel for our planet. But budget constraints left it grounded, a mission without a rocket. Its salvation came not from a new scientific goal, but from a pressing, practical need. The National Oceanic and Atmospheric Administration, NOAA, the nation's official weather agency, required a new watchman. Their existing satellite monitoring the solar wind, the constant stream of charged particles from the sun, was aging out. A failure would leave us blind to incoming solar storms, so a powerful interagency handshake took place. NASA, the master builder, refurbished the DSCOVR spacecraft and provided the launch, delivering it to a special gravitational balance point 1 million miles sunward from Earth. NOAA, the expert operator, then took the controls, running the day-to-day mission and distributing its vital data to forecasters around the world. This partnership is a perfect fusion of two different government DNA strands. NASA excels at the one-time, high-stakes engineering of developing and launching a spacecraft. NOAA specializes in the relentless, operational grind of 24/7 monitoring and forecasting. DSCOVR sits at the intersection, its original Earth-observing camera still snapping beautiful full-disk images of our planet, while its space weather instruments serve as a crucial early warning system. When a coronal mass ejection, a billion-ton cloud of magnetized plasma, erupts from the sun, DSCOVR is our first line of defense. It detects the shock wave in the solar wind, giving utility companies and satellite operators a critical 15 to 60-minute heads up to safeguard their sensitive infrastructure. This is not abstract science. It is a practical shield for the technological backbone of modern civilization. The mission demonstrates how a platform designed for one kind of discovery can be brilliantly repurposed through collaboration to meet an urgent, real-world need, proving that the most valuable space assets often serve multiple masters under a single, vigilant sky. This model of operational partnership, born from the need to protect our infrastructure, finds its ultimate expression in a mission that united the world not for defense, but for pure, unadulterated discovery. That framework for shared vigilance now extends to a new set of rules for a new world. The Artemis Accords are not a spacecraft or a single mission, but something far more profound, a constitution for the next era of lunar exploration. Signed by over 30 nations, these agreements lay the legal and technical groundwork for a sustained human and robotic presence on the Moon. they transform what could be a chaotic land rush into a coordinated, peaceful campaign. The core innovation is interoperability, the principle that a Canadian rover should be able to communicate with a Japanese habitat, and that an Emirati orbiter can share its data with an American lander. This is not just about avoiding radio interference. It is about creating a common language for exploration, from communication protocols to safety standards, ensuring that every piece of hardware sent to the moon can become part of a larger, cohesive whole. This framework is already actively shaping missions. Countries are now openly coordinating their launch schedules and landing sites, ensuring their orbiters and landers complement each other rather than duplicate efforts. One nation might focus a lander on the permanently shadowed craters at the South Pole to search for water ice, while another sends an orbiter to map the mineral resources across the entire region. The scientific data from both is shared, creating a composite understanding no single country could afford to achieve alone. The Artemis Accords represent the ultimate evolution of the partnerships we have witnessed, moving from individual handshakes between 2 or 3 agencies to a global alliance with a shared rulebook. It proves that the greatest challenge in returning to the moon is not the rocket science, but the human science of building trust and common purpose. This collaborative governance model shows that diplomacy is just as crucial as engineering, perfectly paving the way for our final reflection on what all these unlikely unions mean for our future among the stars. These past alliances have rewritten the rules of cosmic discovery, proving that the future of space exploration will be built not by monolithic programs, but by creative, cross-border teams. The next wave of partnerships is already taking shape, moving beyond government agencies to weave together a far richer tapestry of expertise. We are entering an era of deep commercial academic collaborations, where a university's theoretical model for an asteroid mining robot is tested on a commercial lunar lander funded by a consortium of private investors. Public-private partnerships are expanding to confront existential threats, with companies developing the sensitive early warning telescopes and governments coordinating the global response protocols for planetary defense. The most unexpected alliances will draw in industries with no prior space experience. Telecommunications giants are repurposing their satellite constellations to provide high-speed interplanetary internet, creating a data superhighway for Mars rovers and orbital outposts. Terrestrial mining corporations are collaborating with robotics firms to design autonomous excavators that can process lunar soil, turning raw regolith into breathable oxygen and rocket fuel. This cross-pollination of knowledge accelerates innovation at a breathtaking pace. The immense challenges of sending humans to the moons of Jupiter or the acidic clouds of Venus will demand this new model. No single entity can bear the astronomical cost or the technical risk alone. Instead, we will see consortia form, a temporary alliance of nations providing the heavy lift launch capacity, companies building the advanced life support systems, and university labs designing the AI that will guide the spacecraft. As access to space becomes more democratized, the very definition of a mission will evolve. It could be a fleet of tiny sensors built by a high school student network, launched as a secondary payload on a telecom satellite, and providing real-time solar weather data to a global science platform. The ultimate destination, whether it is a distant ocean world or a nearby asteroid, becomes a shared objective that unites disparate groups under a common banner of discovery. The evolution of collaboration points toward a future where the final frontier is not a prize to be won, but a journey to be undertaken by all of humanity together. From Cold War rivals swapping radio parts to modern companies landing on the moon for NASA, this journey through 23 unlikely partnerships reveals a single, powerful truth. Space exploration does not just benefit from collaboration, it demands it. Each handshake, whether between superpowers or startups, has proven that the whole is infinitely greater than the sum of its parts. We have seen how combining diverse perspectives, unique resources, and specialized expertise leads to breakthroughs that would be utterly impossible for any single nation or company to achieve alone. The trajectory of the last 60 years points in one clear direction. The future of unmanned missions will be a tapestry woven from global talent and shared resources. When we finally send probes to drill through the icy crust of Europa, or to sail the methane lakes of Titan, or to launch the first interstellar travelers toward another star, the blueprint for success is already written. It is a blueprint built on cooperation. The greatest cosmic discoveries awaiting us will not be claimed by a single flag. They will be unlocked by humanity itself, united in its enduring curiosity and shared purpose. The final frontier does not belong to one nation. It awaits us all.